So is the screen visible to you?
Yes, sir.
Right. So, so let us say you have a vector space. Okay, you have a vector space. Okay, over a field K. Let us say over a field K. Okay, and let us say that field. Now you are choosing a another field which can be real field, real field or complex field. Okay. And what is inner product? Inner product is a mapping from. Inner product is a mapping from V cross V to this field, real field or complex field. Okay. So for every sorry, I will write U comma. For every U comma V, okay. So U comma V is an ordered pair which is in the element of V cross. For every U comma V, you are associating a element called inner product of U1. Okay, because this field is a field of real numbers or complex numbers. That means obviously this value, this image is either a complex number or a real number, satisfying certain conditions. Okay, so what is that? What are those conditions? First condition is okay. First condition is inner product of okay alpha one or I'll let alpha into u1 okay beta into u2 comma v must be equal to alpha into inner product of u1 comma v plus beta into inner product of u2 comma v. U2 comma that is the first condition. This is called linearity property and inner product. Second condition is inner product of u comma v, and that is true for every u comma v. Okay, that is by default. Okay, for every u comma v, for every u1, u2, and v. Okay, inner product of u comma v is equal to the conjugate, complex conjugate. Okay, complex conjugate of the inner product of v comma e. Inner product of u comma v comma e. Okay, and the third condition is inner product of u comma u is always greater than or equal to 0. Inner product of u comma u is always greater than 0. If at all inner product is 0 for u comma u, that is possible only for u equal to 0. That is possible only for u equal to 0. Okay, so any function which is mapping from v cross v to the field, real field or complex field, satisfying these three conditions is said to be an inner product. Is said to be an inner product. Okay, and if this field is in that, okay, so on the vector space together with the field in this inner product, okay, the vector space together with this function inner product is called inner product space. Okay, inner product space. Okay, so the algebraic structure vector space together with the inner product is called the inner product space. Okay, and this inner product space can be called as a Euclidean space. Euclidean space or unitary space, depending upon whether the field is the set of real numbers or the field is a set of complex numbers. Okay, so if the field is real number, then what is the property of real number? A bar equal to a. Do you agree? Whenever a bar equal to a is a real number, or every real number is having this property. Do you agree? Okay, so if that is the case, then v comma u bar is nothing but okay. In that case, what happens? V comma u comma inner product of u comma v is equal to, according to the definition, it is v comma u bar. But if the output is, if the net product is a real number, then what is a real number bar? What is the conjugate of a real number? This is going to be v comma u only. Do you agree? So for a Euclidean space or for a real inner product space, u comma v inner product is same as inner product of v comma u. If it is a unitary space, then conjugate of a number not necessarily equal to itself, because a plus ib is not equal to b plus a minus ib. Therefore, that is different. Okay. So if you are limiting your discussion to real inner product spaces, then you can put the condition that instead of putting the condition like this, you can put the condition as u comma v is equal to v comma u. If you are limiting the discussion to the real inner products, that means instead of f, if I am considering only real field, then these three conditions are sufficient to see. Is it clear? Shall I proceed? Okay. So for example, you take this one. Okay. Now let us confine our discussion to the Euclidean space. Let V be a Euclidean space. That means I am going to assume this property. Okay. Be a Euclidean space. What is the spelling of Euclidean? D-I-A-N or D-E-A-N? Please tell me the spelling. I-A-N, Euclidean space. Okay. In that case, I can assume this condition. So if I want to find out inner product of two vectors like this, let us say 2u1 plus 3v2, comma 4, okay, u1 minus 5v, 5, okay, I'll call it as u. Okay, 4, okay, 4v1, let us say like this. Okay, 4v1 minus 5v2. Okay, so then how do you find out the inner product of this? This is nothing but I will take the next page. Okay, so something like this, you take an example. Okay, so something like if you want to find out inner product of 2u1, okay, 2u1 plus 3, 4v1 minus 5v2. Okay, how do I find out inner product of this? So this is nothing but according to the definition. Okay, this is not, you see this as a vector, whole vector. Okay, according to the previous property, according to this property. Okay, see this as a whole vector. Constants can be taken out. Okay, u1 into v and u2 into v. That is what the result says. That means what, 2 times 2 times of, okay, inner product of u1 comma 4v1 minus 5v2, okay, plus 3 times inner product of, okay, u2 comma 4v1 minus 5v2. Okay, then if I am considering this as an inner product, then I can interchange these two. Inner product ub equal to inner product vu. Okay, 1 minus 5v2 comma u1, okay, plus 3 times inner product of 4v1 minus 5v2, okay, comma u2. Again according to the linearity, this can be written as 2 times, okay, again apply that linearity product, v1 u1 v2 u1. That means what, 4 times inner product of v1 comma u1 minus 5 times inner product of v2 comma u1, okay, plus 3 times 4 times inner product of v1 comma u2 minus 5 times inner product of v2 comma u2. Okay, so this is nothing but 4 2s are 8. 8 times inner product of v1 u1 minus 10 times inner product of v2 u1 plus 3 4s are 12 times inner product of v1 u2 minus 15 times inner product of v2 u2. Is that okay? So it is like so you can see this as again I can interchange this to 8 times inner product of v1 u1 minus 10 times of I can interchange like this. Again symmetric property I can use because I am considering a Euclidean space u1 v1 minus inner product of u1 v2, okay, plus 12 times inner product of u2 what is this v1 minus 15 times inner product of v2 u2. Again interchange in a Euclidean space. So how it is looking like just multiplying two polynomials. Okay, 4 2s are 8 u1 v1 u1 v1. Okay, u1 v1. Okay, next 5 2s are 10 u1 v2. Okay, 3 4s are 12 u2 v1. Okay, and 3 5s are 15 u2 v1 like this. Okay, and u1 may be equal to v1, u2 may be equal to v2 also. Okay, it doesn't matter whether some these vectors u1 equal to v1 or u2 equal to v2 or anything. It can this is hold for any vectors. Okay, that is how we can write down the inner product. Okay, further you can simplify this because u1 v2 anywhere you have u1 v2 there is nothing like that. Okay, so that is how if some of the terms are same you can combine them and put it. Is this clear up to this point? Shall I proceed? May I proceed? Do you understand what is an inner product and how can we write inner product of two vectors? Inner product has to satisfy these three conditions. If the field is a field of real numbers, then inner product of UV becomes inner product of VU because conjugate of a real number is itself. Shall I proceed? Please respond. If you have any doubt at this stage, please ask me. I'll try to clarify. Then I'll go to the next one. Hello. So you can directly write this step from this. Okay, if you want to find out inner product of two numbers. Okay, there are different ways of defining the inner product. I will come back to that. First of all, you just see the general definition. Shall I proceed?
Yes.
Okay. So if that is the case, then what is the concept is norm. Norm of a vector. Okay, norm of a vector. Okay, if you have an element, okay, if you have an element of V, if you have an element of V, okay, then norm U is defined as under root of inner product U comma U. Okay, norm of a vector is defined as an square root of U comma U. Okay? So this is something like magnitude of the vector. Magnitude of the vector. Okay, and this is possible. Why? Because in the definition we said inner product of U comma U is always greater than or equal to 0. Inner product of U comma U is always greater than or equal to 0. So inner square root is always positive because this is non-negative number. I can always take the square root of the non-negative number. So it is making some sense. Okay. So then what is the distance between two vectors? Distance between two vectors is defined as norm of u minus. Okay, so this is defined as distance between u1, distance between u1. Okay, now what is dot product? Dot product is a special case of inner product. Dot product is a special case of inner product. Let us say u equal to u1 let us say u1 belongs to n dimensional space. Let us say u comma b are belonging to n dimensional space. That means what u can be written as u1, u2 and so on un. Sorry, this bracket. Okay, and v can be written as v1, v2 and so on vn. Okay, so what is u dot v? If I am defining inner product of u and v, okay, so if I define dot product of u and v as u1 v1 plus u2 v2 plus and so on plus un vn. You know how to find out dot product of two vectors for 3 dimensions and 2 dimensions. We are generalizing the same concept to dot product of n dimensional vectors. Okay, so this is called a dot product of two vectors. Obviously it is a scalar, it is a number. u1 is a number, v1 is a number, u1 is a number, u2 v2 is a real number, un vn is a real number. Sum of these numbers is a real number. Okay, now this dot product induces an inner product. Okay, so if I define inner product of u comma v as u dot v. Okay, this dot product will satisfy all the properties we considered earlier. Okay, okay, dot product of this will be equal to dot product of a linear combination is equal to linear combination of the dot products. Okay, a bar dot b bar equal to b bar dot a bar. You know, a bar dot b bar equal to b bar dot a bar whenever we are considering an Euclidean space. Okay, and dot product is always dot product of u comma u is always greater than or equal to 0, and that is 0 only when u equal to 0. You see, if I take u equal to something like a comma b, okay, then what is inner product of u comma u, which is u dot b. According to this definition, this is a comma b dot product with a comma b. So this is something like, you can see like ai bar plus bj bar. Okay, so this is nothing but a dot a into a greater than or equal to 0. This can never be negative. And when u dot u equal to 0, that means okay, so inner product u comma u equal to 0 means what? A square plus b square must be 0. That is possible only when a equal to 0 and b equal to 0. And I said I said a is nothing, u is nothing but a comma b. When a equal to 0, b equal to 0 means 0 comma 0. That means 0 vector. Okay, so therefore we can see this dot product is a special case of inner product. Okay, if you are defining the inner product like this, okay, then this induces a inner product space. Okay, so this is one way of defining the inner product through dot product. But inner product not necessarily every dot product is an inner product, but a inner product not necessarily equal to dot product. Okay, so this is one way of defining the inner product between two vectors. Okay, then what is the angle between the two vectors? Okay, so what is so we are trying to generalize the concepts of vector from dot product to the inner product. Okay, so how do you define the angle between two vectors? For a 2-dimensional or 3-dimensional, we will call it as theta equal to cos inverse of two vectors, let us say u and v. Okay, u and v as u dot v by mod u into mod v. Am I right?
Yes, sir.
Now, what is the generalization to inner product? Okay, suppose u and v are belonging to inner product space. Okay, or Euclidean space. Euclidean space is a vector space together with the inner product. Okay, then how do you define angle between these two vectors? Theta is equal to naturally cos inverse of what is the generalization to dot product? I said generalization to dot product is inner product. That means inner product of u comma v divided by. I said how do we define magnitude of a vector in Euclidean space? Through norm. Can you see that? I said this is the magnitude in Euclidean space. So now modulus of u becomes norm u, norm u into norm of the vector u into norm of the vector v. That's it. Okay. And when do you say u is perpendicular to whenever theta equal to pi by 2, we say that u perpendicular to v. Okay, what we call, you can call it as perpendicular. Okay, so here whenever you get theta equal to pi by 2, okay, we say that u is orthogonal to u is orthogonal to. Okay. Now the set of, there is a result saying that the set of orthogonal vectors, okay, the set of I think your note is hanged. Right. Now there is a result saying that the set of orthogonal vectors are set of or orthogonal set of vectors. The set of orthogonal vectors are linearly independent. The set of orthogonal vectors are linearly independent. Okay. But the converse need not be true. Linearly independent sectors not necessarily orthogonal. You know, okay. Any two non-coplanar vectors are going to be linearly independent. Okay. But so therefore these three vectors are non-coplanar. Therefore they are linearly independent. Okay, but non-coplanar vectors not, and they are also orthogonal. Okay, so these are all orthogonal as well as linearly independent. But so I can have two vectors like this. Okay, I can have two vectors. But there is an angle. Are these two perpendicular? Okay, are these two perpendicular? I have, let us say, these three vectors. Okay, so these two are not perpendicular. These two are not perpendicular, but these three are non-coplanar. Therefore, these three are linearly independent vectors, but they are not orthogonal because there are two vectors which are not perpendicular. Okay, so orthogonal vectors are always linearly independent. Linearly independent vectors not necessarily orthogonal set of vectors. Okay, now the question is the converse. Okay, and we also know, so converse is not true. Okay, so converse need not be true. Need not be true. Now the question is, okay, given a set of linearly independent vectors. Okay, how to generate an orthogonal set of vectors. How to generate an orthogonal set of vectors. And if these set of vectors, linearly independent vectors, are actually, if I say it is a basis, okay, if you are given a basis, then how to generate an orthogonal basis? Okay, now the question is like this. Okay, how to create an orthogonal basis? Okay, now what is orthonormal? So what do you mean by orthogonal set? Orthogonal set, okay, where u is perpendicular to v for every let us say orthogonal set denoted with s. U is perpendicular to v for every u comma v belongs to s. That means what? Inner product of u comma v is always 0. And what is the orthonormal set? What is orthonormal set? It is an orthogonal set. Okay, it is orthogonal set. And where norm of each vector is equal to 1. Norm of each vector is equal to 1 for every v belongs to s. Okay, so norm magnitude must be 1 for every vector. So what are examples of orthonormal sets and orthogonal sets, or what are the examples of orthonormal basis and orthogonal basis? Let us take a simple example, r square. Can you give a basis for r square? Can you give a basis for r square? What is the standard basis for r square? One zero and zero, right? This is the standard basis. What is another basis? You take any two linearly independent vectors. That means if the determinant is non-zero, that means they are linearly independent. Let us say 1, 2. Okay. Let us say 2, 5. Does it work? What is the determinant? 1, 2. Okay. Let me call it as 1, 2, 2, 5. You can see 5 minus 4 is 1, non-zero. Okay. So this is a basis of r square, and this is also basis of r square. Why? Because it is containing two elements which are linearly independent. It is containing two elements which are linearly independent. Dimension of r square is 2, and any set containing two independent elements is said to be a basis. So these two are bases. Okay. Now what is the dot product of these two? 0. Okay, these two are orthogonal. Therefore, this is an orthogonal set. This is an orthogonal set. And not only orthogonal, what is the norm of each vector? What is the magnitude of each vector? Root of 1 square plus 0 square, 1. Root of 0 square plus 1 square is 1. So, this is norm of u is equal to 1. Okay. Therefore, this is an orthonormal set. This is an orthonormal basis. Orthonormal basis. Okay. Whereas here, this is also basis, but what is the magnitude? Dot product is what is the dot product of these two vectors? 2 plus 10. 2, 1 into 2, 2, 5 into 2, 10, 12. This is inner product of our u dot v equal to, which is not equal to 0. So there it is not an orthogonal set. Not only orthogonal set, it is and also norm is also not equal to 1. Norm of u comma 1 comma 2. Norm of 1 comma 2 is root of 1 square plus 2 square. Okay, with respect to the usual dot product. Okay, so this is root 5 not equal to 1. So it is just a basis. This is just a basis, but not a orthogonal basis is not an orthogonal. So this is not an orthogonal basis or not an orthonormal basis. Okay, just a basis. So can you give an example of a orthogonal basis? This is an orthonormal basis. Can you give an example of a orthogonal basis? That means independent vectors. You should have two independent vectors, but norm need not be one. Can I take it as 2, 0 and 0, 2? Or you take another one. Okay, can I take like this 1, 2? Okay, so 1, 2. So 2, 1, 1 minus. Okay, let us take a simple example. 1, 2, 0 and 0. Okay, let us say something like 2, 0 and 0. Okay, these two are linearly independent. Why? Because 2, 0, 0, 2 determinant is 4, not equal to 0. They are linearly independent, and therefore they generate the space because it is containing two independent vectors. But what is the norm of 2 comma 0? Norm of 2 comma 0 is nothing but root of 2 square plus 0 square, which is equal to 2, not equal to 1. So these are all orthogonal vectors, but not orthonormal vectors, because magnitude is not 1. So every orthonormal set is an orthogonal set, but an orthogonal set need not be orthonormal set. So this forms an orthogonal basis. Orthogonal basis. Okay. Now, so if you have a orthogonal basis, it is easy to form the orthonormal basis. Why? You just divide each vector with its norm, then that becomes a unit vector. Okay. So if I have a u bar, how can I create a unit vector? By defining v equal to u by norm of u. Okay. 1 by norm u is a scalar. Scalar into u is a vector, belongs to the vector space. Is that okay? So if you have an orthogonal set, from that it is easy to find out the orthonormal set. Simply divide each vector with a normal vector. Okay. So we have two cases: b1, b2, b3. Okay. Basis. Okay. Orthogonal basis. Okay. Next one is orthonormal basis. Okay, from here to here, this is very easy. Just divide each vector with its magnitude, then you will get orthonormal basis. Now the question is how to find out a orthogonal basis from a given basis. This is the question. Okay, that is through a process called Gram-Smith orthogonalization process. Okay, so what is that? We will see now. Okay, that's the main discussion now. So now I'm going to proceed. So is it clear so far? So a basis can be just a basis can be an orthogonal basis, a basis can be orthonormal basis. Okay, orthogonal basis means where any two vectors are orthogonal. What do you mean by orthogonal? Inner product of any two vectors must be 0. Okay, what do you mean by unit vector? If the norm of the vector is 1, that is called unit vector, and you can always normalize a vector to get a unit vector. Just you divide the vector with its norm, then the resultant vector is going to be normalized unit vector. If u is a vector, this can be called as a normalized unit vector. Okay. So all this information is all about that what we have discussed so far. As you can see now, 3 into 2, 6. Okay. Okay. U1 V1. Okay. 15 U1 V2. 18 U1 V3. Like that you can generate. Okay. Here. Okay. 3 2s are 6. 3 5s are 15. 3 6s are 18. Okay. U1 V1. U1 V2, U1 V3, again 4 2s are 8, U2 V1, okay, 4 5s are 20, U2 V2, and 4 6s are 24, U2 V3. And you can simplify this further. And what is norm of a vector? Under root of inner product of u comma u. Okay, and you can always normalize a vector to get a unit vector. Okay, whenever the inner product equal to 1, that is called unit vector. Inner product 1 means norm is also equal to 1 because under root of 1 equal to 1. You can always normalize a vector, and this is an important inequality called Cauchy squares inequality. Cauchy squares inequality. It says that inner product of u comma v whole square is always less than or equal to, okay. Okay, inner product of u comma v whole square is always less than or equal to inner product of u comma u and inner product of v comma v. Or you can write in terms of norm also. Inner product of u comma v is always less than or equal to norm of u into norm of v. Okay, so remember that result. It's a useful result in functional analysis. And how do you define dot product? You can norm. So this is a dot product, okay, of two vectors in n-dimensional space. Add the multiply the corresponding elements and the add. Okay, and in terms of matrices, you can define the inner product of u comma v as u transpose into v. Okay, so this is another way of defining the inner product. I said dot product is a special case of inner product. That is the only way of defining the inner product. Through this definition also you can define the inner product. Okay, and these are the properties of norm. Okay, norm is always greater than or equal to 0 because norm is square root of inner product. Norm equal to 0 only when v equal to 0. Norm of k into v is modulus of k into norm v. Okay, norm u plus v is always less than or equal to norm u plus norm, because basically norm is a square root. Okay, if you are bringing the scalar from the square root, you have to put a modulus, because you know square root of 4 equal to plus or minus 2, like that. Okay, so the last one is called triangular inequality. Okay, 1 second, let me put my laptop charge. 1 second. Okay, so that is the case. Okay, now from that you can define what is angle between the vectors. Okay, generalization to dot product. Cos equal to u bar dot v bar by mod u into mod v. In a similar way, cos equal to inner product of u1 v by norm u into norm v, and you know cos theta is always between minus and 1. This is the just usual way of finding the angle between the two vectors. Okay, so we are, instead of modulus, we are putting norm. Basically what you are doing is a bar dot b bar by mod a into mod b only. That's how you will get because it is a three-dimensional. Okay, so three-dimensional angle between three-dimensional vector is nothing but through usual dot product. And what do you mean by orthogonal? If the inner product is 0, then they are said to be orthogonal vectors. Okay, and you know 0 is always orthogonal to every vector because inner product of 0 comma v is going to be 0. And these are some of the examples, and this is another way of defining the inner product. Okay, so inner product can be defined through an integral form also. And the question may be, if you want to find out an orthogonal, if you want to find out a vector which is orthogonal to given vectors. Okay, orthogonal means what? Dot product must be 0. So you take a w equal to xyz such that this is orthogonal to u1. That means u1 w dot product with u1, inner product of u1 with w must be 0. Inner product of u2 with w must be 0. Okay, that means what? Dot product of these two vectors are 0 means what? X plus 2y plus z equal to 0, and 2x plus 5y plus 4z equal to 0. Okay, so then you solve the homogeneous system of linear equations. Okay, then you will identify that there are several vectors which are orthogonal to these two vectors, because these two are linearly independent. How many vectors are orthogonal to this vector? Okay, see, if this is this is one vector, this is one vector. These two are, let us say, linearly independent. How many vectors are orthogonal to these two vectors? One vector, two vector, three vector, four vector. So any vector perpendicular to the plane containing these two vectors is going to be an orthogonal to this vector. Therefore, you are going to get an infinite set of vectors which are orthogonal to the given set of vectors. So orthogonal vector, not one unit, one vector. There can be several vectors which are orthogonal to this vector. Okay, so then you will, for a special case, 3 to 1. Okay, if you are giving a particular value, in general we give z equal to k. When you give z equal to k, you will get y and x in terms of k. You know, so solving system of linear equation. If that k equal to 1, you will get one particular vector. So this is a vector perpendicular to this. You can see dot product 3 minus 4 plus 1. 4 minus 4 is 0. Similarly here. And this is a vector. If you want to normalize this, then you will get an orthonormal vector. Okay. You will get a vector, unit vector, which is orthogonal to which is given to. Okay. So I said orthogonal sets and bases. Okay. Orthogonal set, ortho. If any two elements are orthogonal, that is said to be orthogonal set. And if that orthogonal set becomes orthonormal, if norm is 1, that means inner product of that those two vectors is 1 for every pi. Okay. So if S is orthogonal, then S is linearly independent. Okay. So if you have an orthogonal basis, okay, what is orthogonal basis? It is a basis in which any two vectors are orthogonal. Okay, so if you have an orthogonal basis, you can express any vector as a linear combination of these vectors. That means the formulas for the coordinate vectors are given like this. You take a vector v, this is a vector, take the inner product of v with the u1, first element of the basis, divide with its norm of u1, that is the first coordinate value, first coordinate. Similarly, take the inner product of v with the second basis element, divide with the norm of the second basis element, that is the second coordinate, and so on. Find out the inner product of v with the last basis element, divide with its norm. Okay, divide with its square of the norm. Then that is the last coordinate. Then take the linear combination of these elements with these scalars. That is the result. Okay. Okay. So this is what I was talking about. Gram-Schmidt orthogonalization process. Okay. If you are given a basis, okay, one can use this. One can use this basis to construct an orthogonal basis of V as follows. Okay. So this is the question, right? If a basis is given, how to find out an orthogonal basis for the same vector space. Okay, so from this basis we can create an orthogonal basis. Okay, so this is the basis given, v1, v2, and so on, vn is given. From this we are going to create another basis which is orthogonal set. That means we are going to create an orthogonal basis for a vector space. How? First basis element you define as w1. How do you generate the second element of the orthogonal basis? W2 equal to, you define like this. V2, what is V2? Second element of the first basis. V2 minus inner product of V2 with W1 divided by inner product of W1 comma W1 into W1. Okay. So it's a recursive definition. So that W1, W2 will be, and if you find out the inner product of W1 and W2, you will notice that inner product of W1, W2 will be 0. That means that W1 is orthogonal to W2. Similarly, how do you create W3? Previous two orthogonal vectors. Okay, you take the third vector V3 minus V3 inner product with W1 divided by norm of inner product of W1 into W1 minus, okay, V3 inner product with W2 divided by inner product of W2 into W2 like that. Okay, if you have n vectors, repeat the formula up to n. Okay, extend the formula up to n. Okay, so that means to say that each vector, okay, each vector you are writing as a linear combination of the previous vectors. Okay, W3 you are writing V3 minus linear combination of W1 and W2. Wn you are writing Vn minus linear combination of W1 to Wn minus. So Wk you are writing Vk minus linear combination of the previous orthogonal vectors. The formula for CK1, CK2 and so on are given by these inequalities. That's it. So if you find out that, if you apply this formula step by step, finally you will arrive to an orthogonal basis from a given basis. Okay, it's a very important problem in examination point of view also. You may be asked to apply Gram-Smith orthogonalization process to find out an orthogonal basis for the given vector. If you have an orthogonal basis, it is easy to find out the orthonormal basis. Next step is very easy because divide each vector with its norm, you are going to get an orthonormal basis. Okay, so look at this example. Okay, so it is given that a space is this is the basis, okay, for a subspace of this R power 4. Obviously, the dimension of the subspace is going to be 3 because when these three are linearly independent, any three linearly independent vectors generate a space of dimension 3. Two linearly independent vectors generate a space of dimension 2. Three linearly independent vectors generate a space of dimension 3. Okay. Okay, so what is the question? Apply Gram-Smith orthogonalization process to find out an orthogonal basis. To find out an orthogonal basis and an orthonormal basis for a subspace spanned by these vectors. Okay, so you can verify that these three are linearly independent, and once they are linearly independent, you can start finding the orthogonal elements. First element is going to be V1. First one element is going to be V1. How do you compute the second element? Second element is V2 minus, okay, V2 minus V2 into inner product of W1, okay, inner product of W1 by W1 into W1 into W. Okay, okay, what is inner product of W2 with W1? V2 with W1? Okay, how do you compute this? And how do you compute V2 with W1? What is V2? V2 is nothing but a second vector. Okay, so 1, 2, 4, 5. Okay, inner product in our sense dot product with the W1. What is W1? W1 is V1. That means 1, 1, 1, 1. What is the dot product? 1 plus 2 plus 4 plus 5. 9 plus 2 is 11. 11 plus 1 is 12. Simply you are finding the dot product. What is W1 inner product with W1? Inner product W1 comma W1 is nothing but norm of W1 whole square, that is sum of squares. What is W1? W1 is this one. Okay, that means 1 square plus 1 square plus 1 square plus 1 square. What is 1 square plus 1 square? That is 4. That is what is given. That means square of the magnitude. So this is nothing but dot product of V2 with W1 divided by square of the magnitude of the W1 into W1. Okay, then you simplify this. What is V2? V2 is this, substitute. W1 is nothing but V1. Okay, substitute those two vectors and simplify, you will get this. Once you have V2, how do you find out V3? V3 formula, W3. W3 is nothing but V3 minus again V3 inner product W1 by inner product of W1 into W1 minus V3 dot product with W2 by square of the magnitude into W2. Okay, so what is V3? V3 is this vector minus dot product of V3 with the W1. What is W1? V1 divided by square of the magnitude of W1 minus dot product of V3 with the W2. Dot product of V3 with the W2. What is W2? W2 is here. Find out the dot product of these two vectors. Divide with the, okay, square of the magnitude of W2. What is the magnitude square of the magnitude of W2? What is norm W? What is W2 dot product? This is nothing but minus 2 whole square plus minus 1 whole square plus 1 square plus 2 square. That means what? 4 plus 1 plus 1 plus 4. 5 plus 5 is 10. You can see this here. Okay, multiply with 2. Okay, then substitute the vectors. Substitute these vectors. V3 is this. W1 is this. W2 is the previous vector. Substitute those vectors, you will get a vector. So this W1, W2, W3 forms a orthogonal basis. Okay, if you are dividing each vector with its magnitude, okay, first magnitude is under root 4 is 2. Okay, second magnitude is under root 10. Third magnitude is under root of 9, 10. So if you are dividing with its 2, if you are V1 by norm V1, what is W1? but U1 is nothing but W1 by norm W1. That means magnitude. What is U2? W2 by norm W2. Okay. And what is U3? W3 by norm W3. Okay. So this forms, okay, U1, U2, U3 forms in ortho normal basis. W1, W2, W3 forms in orthogonal basis, and V1, V2, V3 forms a basis. Basis is given. From this we found the orthogonal basis. From orthogonal basis we created the orthonormal basis. Okay, so that is how we compute the orthonormal basis from a given set of linearly independent vectors. So is this process clear to you? Okay, so it's an very easy to apply. It is nothing but dot product and finding the magnitude. You remember the formula and substitute in the formula. Okay, so it may show you the syllabus on this. So in this we have completed all these parts. Okay, linear transformation, vector space, dot product. Dot product is a special case of inner product, and orthogonality also we completed. Okay, so rank nullity theorem, vector spaces, dot product, linear transformations, all these things are over. Okay, so what is remaining is SVD and PCA, principal component analysis. Okay, so next concept is principal component sorry, singular value decomposition, SVD, for which you need the knowledge of eigenvalues and eigenvectors and also diagonalization. So before coming to the next class, you just go through how to find out eigenvalues and eigenvectors, and what are the conditions for a matrix to be diagonalizable, and what is the procedure to diagonalize a given matrix. Okay.